Hello, this is Philip Myers of PEMI Consulting. Today I'll be discussing a practical model for estimating cumulative product release from a corrosion hole in fixed equipment, like piping, underground tanks, and flat-bottom tanks. This presentation introduces a simple, time-dependent geometric model. It also addresses a common regulatory and forensic gap: how corrosion defects actually evolve over time, rather than assuming today's geometry existed indefinitely. Bottom corrosion holes can exist undetected for long periods of time, sometimes years before discovery. This is especially true for buried piping, underground tanks, and flat-bottom tanks. In regulatory practice, cumulative emissions are often back-calculated using the present-day hole size. In at least one enforcement action, the emissions were estimated over a 5-year period using the final hole size from when they believed the tank started to leak. The issue is that this assumption significantly overestimates the release volume. The work is relevant to several groups. Regulators may find it useful for more defensible estimation of cumulative emissions and compliance impacts. Owners and operators can use it for realistic post-event exposure assessment and liability understanding. Engineers and risk assessments can apply it for bounding scenarios and reducing uncertainty, while litigators and technical experts may use it to reconstruct historical release rates during dispute resolution. The model starts with a point at the center of the half sphere, which grows radially at the corrosion rate. The algebra is quite simple. You are attempting to find the value of little r, which is the radius of the hole in the bottom. Time is defined from the moment the corrosion cavity first breaches the bottom plate and leakage begins. After solving the geometry for r, then the expression for hole radius and area are determined. This animation illustrates the growth model concept. Initially, corrosion progresses beneath the plate without leakage. Once the hemisphere reaches the bottom surface, a hole forms and begins to expand radially. This highlights why assuming final hole size existed for the entire period is physically incorrect and overstates the total leakage. The key result of this model is that the hole area grows approximately quadratically with time once breakthrough occurs. Time theta is measured in days, C is the corrosion rate in inches per day, N is the nominal thickness, and R and A represent the hemisphere radius and area of the hole respectively, but any consistent set of units can be used. These plots are based on 5 mils per year corrosion rate, 1/4 inch bottom, and time in days. The plots are based on 4,000 days, or a little more than 10 years. At 10 years, the hole has a radius of about 0.16 inch. Note that the area growth is nearly linear over this time range. This plot shows a cumulative release of liquid with time. In 1 year, a cumulative released volume of approximately 150,000 gallons under the model assumptions. In summary, corrosion holes evolve over time, and explicitly accounting for that growth can materially change cumulative release estimates. For the examples shown, assuming the final hole size existed for the entire period overstates the cumulative released volume by approximately a factor of 2. Even a simple geometric growth model provides a more technically sound basis for regulatory, engineering, and legal evaluations than assuming a constant, fully developed defect. The paper is archived on Zenodo and is accessible via the reference link. The paper will also be shared via LinkedIn for professional dissemination. Thank you.